Okay, guys, the next topic is vectors in space. And the best way to show you vectors in space is to use a 3D graphing calculator. So I'm here at geogebra.org, where there are all kinds of good mathematical apps and tools and graphing calculators to help you with all of your mathematical pursuits. I would recommend checking it out. I use these apps all the time as a teacher, and I recommend you check them out. Anyway, let's graph a vector. And the way you do that in GeoGebra is you type vector. You click this, and then you type in the endpoint of that vector. So let's just stick with a two-dimensional vector, 2, 3. So right now, let me rotate this so it's in the correct orientation. So my x-axis is red, and my y-axis is green. And right now I have the 2D vector 2, 3. Now you're used to seeing this with pointy brackets. In this case, it just has curved brackets like a point. That's okay. We can see that it's a vector here. Okay. Now I'm going to add a third component by adding another comma and then typing in another number. Let's say 4. Okay. You might say, what the heck? My vector hasn't changed. It's still just a vector 2, 3. Well, that's because we can only see two dimensions right now. We see the x-axis and the y-axis. The reason we don't see the z-axis is because it's pointing straight at us. It's this dot right here. Okay, that's actually an axis. We just can't see it because we're looking straight at it. Now when I rotate this view, we're going to see that third axis, but I want to warn you, we're about to move from a two-dimensional world into a three-dimensional world, so brace yourself. Are you ready? Here we go. Ta-da! Here we are in 3 dimensions, and we have a 3-dimensional vector, the vector 2, 3, 4. It goes 2 in the x direction, it goes 3 in the y direction, and it goes, guess how far, 4 in the z direction. Okay, so we have this vector in 3-dimensional space, and it is pointing into the first quadrant. Oops, hold on. Quadrant, that's a 2-dimensional word. With our XY plane, we have 4 quadrants, but now we're in XYZ space, 3D space. Is it called a quadrant anymore? And how many are there? How many sections are there of this 3-dimensional space? Well, if you said 8, you'd be correct. Okay? If you see that there are 4 quadrants on the top half of the z-axis, not quadrants anymore. If there are 8 of them, what are they called? They're called octants. Okay? So we went from quadrants in 2D, now we have octants in 3D because there's 8 of them. 4 on top of the z-axis and 4 on the negative side of the z-axis. And if you have a hard time seeing those 8 octants, I have a picture that I found here of what that looks like. Here's our XY plane. And then when you throw in this z-axis here, coming straight out of the origin of the XY plane, this green plane is the XY plane, but then when you add this z-axis, you get 2 more planes. You get the XZ plane, which is here in yellow, and you get the YZ plane, which is here in blue. So you add 1 more dimension and you get a bunch more, 2 more planes and 4 more sections of your graph. So now you can see the 4 octants on top and the 4 octants on bottom. It's kind of like the rooms of this weirdly shaped house, right? You got 2 floors. The top floor has 4 rooms and the bottom floor has 4 rooms. But of course these planes go on indefinitely, infinitely, right? We just see one section of them. Okay, so we're in 3D space now. Anyway, let's go back to our graph here. So there is our 3-dimensional vector, 2, 3, 4. If I want to point it into a different octant, what would I do? I just need to make one of these negative, right? Because right now I have positive x, y, and z components, so I'm going in this positive octant, right? But if I wanted to go, let's say I wanted to go below the xy plane down here, where z is negative, right? I would just change my z component to a negative value, like -4, and now my vector is pointing down into an octant that is below the xy plane. Okay, so I could point this vector in any direction I want to, and I can have it be as long as I want to just by changing the values of the components, right? With a 3D vector, you can calculate its magnitude. You can do anything that you want with a 2D vector, you can do with a 3D vector. You can project it onto a 2D vector. You can calculate the angle between 2 vectors in 3D. Everything that you do in 2D, you can do in 3D and more. Okay. Speaking of things you can do in 3D, I want to show you something cool. This is not about vectors, but it's just something interesting here. Actually, hold on. I want to show you something first. If I hit enter here, you'll see that GeoGebra actually writes the vector as a column, x, y, z components vertically like this. That's how you'll see vectors written in higher math. This is actually a matrix a 3x1 matrix. And it turns out that you can do all kinds of stuff with vectors if you write them as matrices. So if you see a column like this, that's just a vector. It's the same thing as writing a vector horizontally with commas with pointy brackets. That's all that is. Okay. Anyway, I want to show you something else that's kind of cool. I'll delete this for now. If I graph the graph z equals x squared, okay, I get this parabola. Now if I look at it from the perspective where now my y-axis is gone, okay, my y-axis was pointing straight at me, and I just have my x and my z-axis, it just looks like a parabola, right? And that makes sense because it's just a parabola z equals x squared. X is my input or my independent variable, and z is my output or my dependent variable. And since y is not a part of this equation, y could be anything it wants, right? Y could be any positive value or any negative value. This green axis is the y-axis. Okay, so I get this parabola that's been stretched in the y direction. Okay, interesting. But if I ignore the y-axis and just look at x and z, it just looks like a parabola. Okay, like I'm used to seeing. Now, what if I typed in, instead of y equals x squared, if I typed in z equals y squared? Now I get a parabola in the yz plane. And x could be any value it wants. So I get this parabola stretched in the x direction. And then, of course, if I go with our good old friend y equals x squared, now if I look at my xy plane, well, you can't see it because it's too thin. You see I have the same old parabola, the y equals x squared parabola. It's just been stretched in the z direction. Okay. Last thing I'll show you, and this is all just for fun, these graphs I'm showing you right now, is what if I wanted to do not just z equals x squared, but what if I added in a y squared here? What do you think would happen there? I get a paraboloid. Okay, it's a parabola in any direction that I look at it, perpendicular to the z-axis. Okay, so this parabola, of course, the paraboloid, of course, goes up forever. That's why the edge is kind of blurred to indicate that it goes up, up, up infinitely. But there you go. That's a three-dimensional parabola called a paraboloid, and there's its graph. Okay. So that was just to kind of challenge your intuition a little bit. I would recommend, if this is interesting to you, hop on here to GeoGebra 3D Calculator and start typing in equations with x, y, and z and see what happens. Graph a trig function, graph a higher order polynomial, graph a circle, an ellipse, see what you can come up with here, and I bet you won't be disappointed. It'll be a lot of fun.